Okay, so what I wanted to talk about here was just some ideas in eigenfunction concentration. So the kind of problems I'm looking at, you have an eigenfunction uj, and I'm going to denote the eigenvalue by lambda j squared. And I'll assume that we're on a smooth manifold and at least localized away from the boundary. What I'd like to know is how large can eigenfunctions get? So particularly what's their L infinity norm, and then what are other LP norms? So these are some examples of features you might see locally on an eigenfunction. The first is a point-like concentration. So this has very high L infinity norm, but because it's only very big over an extremely small area, so as you start to take other LP norms, you get quite a sharp drop-off. Another really common one to see is a tubular concentration. So this one has a lower L infinity norm, but you get a bit more spatial concentration. And completely over the other end, you have something which has a very low L infinity norm but is spread out spatially. So instead of studying eigenfunctions in this setting, I'm going to actually move into the semiclassical setting. And for the purposes of this talk, I'm going to only talk about the semiclassical setting in Rn. Everything can be transferred across to a manifold pretty easily. So here I'm encoding the energy of the system into the operator itself. Now I've added in a potential v of x. For functions v of x that don't have any h dependence themselves, this is trivial to add these in and consider them as well as Laplacian eigenfunctions. So just do a little bit of rearranging here, and I introduce the semiclassical parameter, which is 1 over the eigenvalue lambda. So now I've got the operator that I want to work with, and along with the operator you get a whole set of symbols. And the thing to keep in mind, and which is really important for this talk, is that multiplication goes to a scaled differentiation. So if you want to think of that as like a scaled Fourier transform statement. So the whole point of this is that we get a symbol p x xi where the principal symbol for the Laplacian is xi squared. So we're taking things that are oscillating at speed lambda inverse, and we're scaling that to be 1 and encoding the energy elsewhere. And just for interest's sake, you can define a whole calculus of operators with the symbols, and it looks very much similar to the usual pseudo-differential calculus. The only difference are these scaling factors. Now, the semi-classical notation is meaningful in the sense of intuition, and intuition guides what we think is going to happen. So on one side we have quantum mechanics, so we describe a system quantum mechanically. In the notation that I use, that's like saying that U satisfies this semi-classical differential equation. And we then interpret U as being a stationary state with energy h to the minus 2, and the L2 mass is considered to be some kind of probability. Now then we have the classical mechanical description, where we say, all right, we're not talking about probabilities anymore, we're talking about a trajectory. And we can, from a starting position, we can solve for all time and describe the motion of the particle through phase space. And heuristically, because they both describe our world, we expect that there is some kind of relationship between them. So we would expect to see something of the classical mechanics in the quantum mechanics. Now, as far as eigenfunction concentration is concerned, what I really want you to think of is little packets tracking a long trajectory. So if we have a classical trajectory, we see a little packet which has, some localization, and we want to think that at least for short time, these little packets are going to follow along the trajectory pretty nicely. And that is reasonable, and one of the big technical difficulties is determining how long you can run time and make this reasonable. So the first set of estimates I wanted to discuss today are due to SOG, and these are whole manifold estimates. So it's taking an eigenfunction, you measure its LP norm over the full manifold, and you get a power-like growth. Now, this delta NP, I've plotted it here, delta against 1 on P. It's piecewise two different regimes. So I showed you the point and the tube concentrations, and they're very important. The point concentration is the concentration that gives you the sharp examples for high values of P. And so everything, the worst thing you can have, behaves like a point until you get down to this kink value. Then the regime changes, and it's the tubular concentration that will optimize the LP norms. So you should think of these two as the sort of bad cases, and they completely describe the behavior. At the kink point, they're both sharp for this estimate, and there's an entire family of things between them that is also sharp. So a lot of the difficulty in this area is determining that kink point. So Sog's estimates are actually for spectral clusters, so he allows sums of eigenfunctions of similar eigenvalue. And we always have to do something like this because uncertainty makes it very hard for us to pinpoint an exact eigenfunction. So these are sharp for clusters, and if you have high multiplicity, say spherical harmonics, you can actually find eigenfunctions that locally look like a point or locally look like a tube. Now you can move this over to a semi-classical statement, and that's by Koch-Tartaru and Zworski. So in that case, your statement then becomes that U approximately satisfies the differential equation. So if it was an eigenvalue, I would say Pu is equal to 0. I'm allowing some order H tolerance. And that's the same as allowing that spectral cluster and sum of similar eigenfunctions. And now in this case, you obtain the same set of estimates for U in terms of its L2 norm. And the conditions you require are on the symbol, so you get a little bit of a bigger class of operators than simply the Laplacian. So you require that at the point where the symbol is 0, desire is not 0, and you have a curvature condition. And both of these are very important. So I'll sort of refer to these as Laplace-like operators. They have similar dispersive properties to the Laplacian. Now once you've considered whole manifold estimates, you can start to look at hypersurface or submanifold estimates. So this is where we'll take just a cross-section of the eigenfunction, restrict it down to a lower dimensional object, and measure the LP mass on that object. So Berkshire and Zvetkov in 2007 did this for the Laplacian eigenfunctions. They obtained two different sorts of regimes depending on whether you're on a hypersurface or a lower dimensional submanifold. So hypersurface is more interesting because it still has this piecewise behavior with two different regimes, the point and the tube. So the same kinds of eigenfunctions are still sharp, but this kink point has moved. So although you still get this sharp example, you have it at different values of p. For submanifolds of lower dimension, these point-like concentrations are big enough that they're always a sharp estimate. So there are still tubular estimates in here, but they're always somewhat better than what you get out of the point. So the behavior here is just a little bit less interesting. Now the work I've been doing is on extending that submanifold and hypersurface estimates into the semiclassical regime. So what I obtained is in the same setting as Koch-Tartaru and Zworski, we allow order H tolerance, that you get exactly the same estimates as Berkshire and Zvetkov. So these are the estimates that you obtain for the semi-classical operators. And you have similar Laplace-like conditions here. The first condition is exactly the same. Second condition is a little bit stronger. I require positive definite second fundamental form rather than just curved. Now that's because I'm going to, technically when you're proving the estimate, you need to take cross-sections of this hypersurface. And every cross-section is itself curved. That's the reason for the slightly stronger assumption. Now, key to all of these estimates is introducing an evolution operator. So this comes out of the first condition. So we say the symbol is 0, it means desire is not 0. So we can factorize the operator into an EXI. Now E we consider to be completely harmless. Don't really worry about that. What's the main part of this is the xi I minus A. Now when we quantize that, we can tell exactly what operator we get out of the xi I part. We get HDXI. Then we have some semi-classical pseudo-differential operator A. Now we're going to call this an evolution equation. We say, all right, let xi be our time variable. And if it is the time variable, then we can call this a nice evolution operator, and we can solve and find a solution operator u. The other thing to note about this xi I is we also say that this is the principal direction of oscillation. I'll just show you what that looks like for the Laplacian on Rn. So the Laplacian on Rn, symbol is 0 on the sphere of radius 1. So what we're doing is we're localizing around some xi naught on the sphere. We're considering a little ball around that and creating a packet which is localized so its principal direction of oscillation is about xi naught. then we'll call that direction time. So we're seeing this just moving along for short time. It will look something like a packet oscillating in xi-naught direction. So time is the principal direction, and now we need to consider how that interacts with the hypersurface. We're only going to talk about hypersurfaces now because submanifolds are somewhat easier. So the first case is if you have the hypersurface and you have your principal direction which has some normal component. So in this case you should think of a little packet just passes directly through the hypersurface and moves along its way. So we don't expect there to be much concentration. Our intuition is the most time this packet spends in an area, the bigger the concentration. And in fact, we find that you can actually get quite good bounds for this. So we can say that in that case, because we've created this sort of false time, that U restricted to the hypersurface is a time slice of the solution. And time slices are L2 bounded. So what do we say? Well, it says that U restricted to the hypersurface is its L2 mass is bounded by the L2 mass on the whole manifold, which is about as good as you can get. So this is the easy case, and it is always resolved by the point concentration. The hard case is where you could have your trajectory moving right along your hypersurface. So it could be trapped inside the hypersurface and the packet could spend an awful lot of time there. Now in this case, we treat it as a Strickhart's estimate. So Strickhart's estimate gives us a weighted space-time estimate, and remember that time is this spatial direction. So if we set the weights of the Strickhart's estimate to be equal, the numerology will give us one perfect value of p for which this expression is bounded. So we find that perfect value of p. And that perfect value of p is the kink point, 2n on n minus 1. That is exactly the point where you have this family of sharp estimates. Now the L infinity norm is exactly the same as it is over the whole manifold. You can always get a point, so I can link these in by interpolation. The L2 estimate you just need to do directly. Some kind of almost orthogonality argument will get it for you. It grows in terms of h to the minus a quarter, and then interpolate from the kink point to get all of the estimates. And you can show that the tube and the point are sharp here, so you know that you're done. Now, I didn't make any assumptions about the hypersurface in any of that. I allowed, for instance, a trapped trajectory. So I allowed something like this, a trajectory that stays on the hypersurface. But you could have something intermediate. So you could have something that glances against the hypersurface like this. Now this is not as good as the one that passes directly through. This, in terms of the mechanics, you say its acceleration is non-zero at the point on the hypersurface. So we expect this to be a little bit better, and that is in fact what you find. So in their initial paper, Berkshire and Svetkov did this for Laplacian eigenfunctions, and then Hu extended it into the higher dimensional case. Then for the semi-classical case, it's a result of Hassel and myself. So we start here at the kink point, we obtain a slightly better L2 estimate, and we can interpolate between. We don't expect to get anything better up here, because this is where the point concentration is sharp, and just locate the point on the hypersurface and you're done. So this is the full picture for our hypersurface when you count the geometry in as well. Now the only other thing that I wanted to say with this is that I've assumed order H tolerance. So I'm allowing some pretty bad quasimodes. Now, in the case that there's high multiplicity, such as the spherical harmonics, you can find eigenfunctions which really do have this behavior. However, not many systems have that kind of really high multiplicity, and in those systems, having an order H quasimode means you're allowing a bit of pollution from eigenmodes that have a very similar eigenvalue, but it's not exactly the same. So in fact, it's expected that all of these estimates are much better in cases, say, where you have negative curvature or anything else that will cause the multiplicity to drop. And that's pretty much what I'm interested in now and have been working on recently. So I think I'll stop there. They're all straight lines. Yes, at this point, yeah. This is the full red and black together are not a straight line.
What do you get in the negative curvature?
So the negative curvature setting, you get a log improvement. So it was known that you got a log improvement on the L infinity. I can get log the same, so it's log to the half improvement on the L infinity. I can get a log to the half improvement right down to the kink point, but still working on exactly ironing out the kink point. But believe that you can get the kink point. Under the kink point, Sog and Zeldich have shown that there's a little O improvement, but they don't have a rate.